once we get. Great, thanks, Mac. Sounds like an exciting and packed agenda. So I think people are going to keep joining for the next few minutes, but let's go ahead and get started. And so today, as we all know, it's Buildings and Energy Day. So thank you guys for coming with so much to talk about and to take the full hour. And I'm certainly looking forward to it. So over to the Buildings and Energy team and in the order you just discussed.
Okay, yeah, thank you, Ben. So today, we're happy to share some of our progress from the team. We're going to start from our student researchers and come to more senior, from national lab or from the faculty side. The first speaker is Erna from Penn State. She's a PhD student in the Department of Architecture.
So share screen. So, hi everyone. My name is Elnaz, and my research topic is about the impacts of urban density and future construction on building carbon emissions. And my approach is a bottom-up modeling approach. So, about the background of my research and the problem statement about more than 1,000 buildings in Baltimore have been built in 2023. In comparison to previous year, 2022, so there were an increase like 100 buildings, and there were more than 6,000 new houses were built in Baltimore in 2023, both in multifamily category and single-family houses. So there is a housing demand in Baltimore, and also Baltimore's comprehensive master plan targets at 60% of GHG reduction by 2030 and carbon neutrality by 2045. And also about 64% of embodied carbon emission in Baltimore relates to building sector. So there's a necessity for urban scale analysis of energy usage and carbon emission. So the primary research objective of my research is to investigate and understand the influence of future construction and urban density on both operational and embodied carbon. And my secondary research objective is to understand the trade-off and relationship between densification and subsequent changes in morphological parameters such as floor area ratio and how it's going to change by adding heights to the buildings and floors to the building. And next is to understand the impacts of envelope retrofitting scenarios to achieve energy efficiency and low carbon. So here's an overview of my methodology. First, I collected some 2D footprints of the building and from available sources, and I didn't have the heights of the building, so I used open source real property data of Baltimore, and then I collected other data such as window to wall ratio. So these three data, building geometry, data, building non-geometry, and weather data, I collected all of them as necessary inputs for bottom-up modeling, and then I combined all of the data in ArcGIS software with a spatial join and using longitude and latitude of the building. And then I performed archetypy and I modeled the neighborhoods in modeling and simulation software of Rhino and Grasshopper, and I analyzed the results. So here's the overview of my methodology, and I have developed my methodology, but the neighborhoods that I select, and in some cases it might change a little bit because this is an ongoing research. So phase one of my research includes horizontal understanding horizontal development and urban sprawl. So in this phase, I selected 3 different neighborhoods in R1, detached and single-family houses, and residential R8 attached mid-rise apartments. So I wanted to understand what is the difference between these between these neighborhoods regarding block configuration and the impact of block configurations and distances between buildings and number of buildings per area on energy consumption and carbon emissions. So in this analysis, I understood that with a similar total building footprint area, the higher energy consumption occurs as the number of buildings increase per area of the land. So this is in accordance. This is similar to the literature review that we already have. So by increasing the number of buildings in land of area, the energy usage will increase. And phase 2 of my research is vertical development and urban densification. And the focus in this research, in this phase of my research, was to understand what would be the impact of increasing the heights of the buildings. For example, I analyzed neighborhood of Care, which is an R8 attached mid-rise apartment. And in this analysis, I wanted to understand what is the impact of increasing heights of the building. In base scenario is the current situation with assuming it's just some what if scenario, assuming there is new construction, and the floor area ratio here is 0.65, and in scenario 1 I assume 50% increase of height, which floor area ratio increased to 0.95, and the heights of the buildings are changed in these two scenarios, maximum building height. And the results of this analysis showed that the operational carbon and total energy carbon increased by adding floors, but embodied carbon increased as well, but the amount of increase was like 5%, and this is because the foundation and anything else in the foundation of the building has been already built, so it's just the walls of the building. So we can see that there is like less embodied carbon increasing by adding 50% one floor to the building. So this can suggest like a densification can be an opportunity in these areas of R8 building. And next steps in my research would be to understand different wall sections and retrofitting envelope retrofitting scenarios, the impact of adding insulation to these old buildings of pre-1940, and how these different installations change the urban embodied carbon and operational carbon and energy, and how this differs from new construction. And these are references, and thank you.
Thank you. Any questions?
Thanks, Elnas. Just a clarifying question. You probably said this, but on a bunch of the earlier slides, you had a percentage energy burden. And I realized I wasn't entirely clear what you meant by percentage energy. Yeah, so like there, like this, for example, what does that 5%, 2%, 6% mean?
So energy burden means that how much each individual person in how much residents pay for energy bills. So in R8 residential attached mid-rise building is more than R1 single detached buildings, because they pay more for energy bills, energy utility bill. And this is because in this area there are some old buildings pre-1940, and insulation is not good enough to keep warm inside, and the transfer of heat is much, so they pay more heat for that.
Got it. So is it percent of what? Like, is it relative to the income in that neighborhood, or just percent? Like, what's the denominator?
Sorry, can you repeat your question? I didn't get it.
So it's a percentage. So percent of what? Percent of the average income in that neighborhood? Percent of?
Yes, a percentage of energy burden in that census tract.
So if it's a poorer neighborhood, that number could be higher even if the absolute energy consumption was not.
It's based on the income of the people and energy utility.
Okay. Great, thank you.
Yeah, so just to add, Ben, what is the energy burden is percentage of income that a person spends on utility bill. So this is basically in Forest Park, for example, 5%, an average person would pay 5% of their income on utility bills. Anything above 6 is considered great energy burden, and anything above 10% is considered severe energy burden.
Thank you.
Okay, excellent. I think for the, because of the time reason, let's move to the next one. And I think we have Alex from Morgan State University, also a PhD student.
Hi, everybody. Yeah, let me share my screen. Can you see my screen?
Yes.
So, well, this is the title of my research, Urban Climate Resilience through Green Buildings and Infrastructure. So in my research, I have several studies. So this is my study 3. The first one was kind of like an urban study of Baltimore on this macro scale compared to DC. DC has lots of integration of, has a heavy integration of green infrastructure, heaviest areas. So I'm trying to study what goes on there and try to bring maybe the best practices to Baltimore. Yeah, so this is, let me move this. So this is kind of like the problem statement: high impervious areas, increasing stormwater runoff, heat islands, and like the energy demand from buildings. But at this stage in my research, I'm trying to monitor what happens outside the building and inside, although heavily it leans on outside, the heat and stormwater runoff, which brings us down to like this, my Venn diagram here, which analyzes climate adaptation, mitigation, and the energy efficiency of buildings. So yeah, so first off, stormwater management. At this stage, I'm trying to extend the research to, said earlier, to monitor not just outside. Originally, it was just outside, but I want to monitor what happens inside the buildings, which brings us to the energy efficiency and the carbon footprint life cycle analysis of the research. But I'm not there yet, which is what I'll need maybe collaboration from the team. If I can get any help would be good. So first off, I start with what a green building is. According to the USGBC, they said this focuses on the relationship between the built environment and the natural environment. That means integration of green infrastructure with our regular conventional buildings. So we go on to, so most times when you see green buildings in an area, it kind of takes this form, this kind of shape, where with green buildings come green infrastructure. So in an area that has a green building, it's probably going to have, it always looks like this. Yeah, and it comes with benefits: clean air, food, water filtration, flood prevention, noise reduction, recreation, climate regulation, reduced energy consumption. Yeah, more. So this is my methodology. My case study for this study is the American University. It used to be a huge car park in the past, there in 2010, and then it was transformed into this LEED certified building, LEED Gold certified building, 4 buildings there with heavy green infrastructure. Yeah. Okay, so these are the green infrastructures that were integrated in it. It had bioretention, it has lots of trees, but I didn't include the trees, permeable pavements, and green roofs with all their areas over here. So this is how it was before. So before pre-construction, so it's 7% impervious, had store a high. Looking at it, the asphalt had like a 0.9 runoff coefficient, meaning heavy flooding probably take place there. And high, the heat island was very high. So moving on, so post-construction, this is pulled from like a kind of like an NDVI from GIS. So it had 1% compared, like this is highest impervious surface to pervious surface. So 1 to 3.5. So it's reduced by approximately 70%, I think, yeah. So from 90% imperviousness, yeah, so it reduced to 25% imperviousness, with the other 75 being accounted for, like for the green infrastructure areas. So lower runoff coefficient means better water infiltration and escaping the downstream flooding. Yeah. Okay, and the heat islands too. Okay, we'll get there in the next slide. So this is what I pulled off. This is what I pulled off from the analysis. So the impervious surface dropped to 25%. So what this research is trying to do is to try to correlate what happens by reducing impervious surface to better stormwater management and also heat islands. DC plans on being carbon neutral in 2030, and heavily they lean on green infrastructure for that. That's at the beginning of the research. I said something about climate adaptation, yeah, where you can try to get nature to fix itself rather than the mitigation strategies we have. Yeah, so looking at this, yeah, so reduction in impervious surface to 25% runoff reduction was achieved, and then here 2010, yeah, the temperature of the asphalt was 115 Fahrenheit. In 2020, you see the asphalt greatly reducing because of the green infrastructure all around it. The high albedo roof reduced 4 degrees Fahrenheit. Vegetative areas to reduce. The vegetative areas, these are the areas that had the green infrastructure in it. And in the nearby vegetative areas, the climate, because of the trouble we have with the climate, it's always the heat islands increase every single time. So in 2010, the nearby vegetative areas around the building, when it was a car park, was at 99. So now it is at 107. But because of the heavily integrated green infrastructure in this particular site, you see it even being less than the nearby vegetative areas. Okay, so this is explains the role of LEED in urban resilience. So LEED is the certification body from USGBC that certifies green buildings. And most times you earn, the points are given to them based on the contribution. So we have water efficiency. And if you look through this, that the specific LEED credits achieved, they are almost average in energy and atmosphere, water efficiency, the indoor environmental quality. So for this LEED Gold certified building, kind of leaned on the sustainable side, which is almost achieving almost all points there. So with their green infrastructure, they were able to decide the quantifiable contributions they had. Energy savings of, although these are implied, this is what this said, but not proven yet, achieved a 25% reduction in energy consumption. Yeah, 500,000 gallons of water annually was saved through like efficient fixtures. Yeah, so okay, yes. Okay, so these are my recommendation. Yeah, scale the green infrastructure in urban planning. Although I know Baltimore already has the Baltimore Green Building Standard, but it's not really as strict as LEED, but almost the same thing. So the research is still very much going on. And then, but this is my study 3D. Fourth study kind of leans on maybe a lesson learned register from, because most of this work, most of my work is quantitative. So I was thinking of having this qualitative research where I get the lesson learned from most of the stakeholders that have carried out this research on the problems they went through, and then maybe try to bring that in for, those are my implementation strategies, but this is for the next phase of my research. Yeah, so this is just a summary conclusion. Yeah, so reduction of impervious surfaces, impervious surface by 72%, stormwater runoff mitigation by 43% reduction in stormwater, and then the urban heat island reduction, 2% in the asphalt car park, 4% in the albedo roof area, 7% in the vegetative area. Yeah, that's it. Thank you.
Excellent. Yeah. So thank you for keeping on track. So any question from the audience? Okay, I just have maybe comments. So I used to work with affordable housing community in Boulder while I was in Colorado. So the community leader told us that they want to practice LEED, but they are not pursuing LEED certification because it's very expensive, right? They want to save every penny to the affordable housing. So I see your recommendation. I think, yes, it's good to practice LEED, but certification maybe,
Yes, I know with the I know which is good here for Baltimore now. I know there's a little, not compared to DC, but they have green infrastructure integration here. So now they have the green building standard that is not really as expensive and as strict as LEED.
Okay,
So
great.
that's something to look into.
Excellent. Thank you.
Thank you.
Okay, yeah, let's move next. Also, Tasnim is also a PhD student in architecture at Penn State.
Hi, good morning, everyone. I joined a little late because my TA class was going on, but yeah, thank you for giving me this opportunity. So I am working on selection of effective urban heat island mitigation strategies for a neighborhood in Baltimore and decision-making approach to combine computational modeling and community interaction. So I'm not exactly working in the like at the building level, but it's very important to understand the neighborhood. So my goal is to understand what are the most efficient in terms of increasing outdoor thermal comfort and decreasing the outdoor air temperature, and also making sure that's accepted by the community. But for today's meeting, I'm focusing only on the simulation part, and for any other meeting, I will share my community engagement activities. So in different ways, we can do these mitigation strategies selections, like the variables can be changing in albedo, changing in green infrastructure, or changing in blue infrastructure. And while we are seeing it at a neighborhood scale, it's like it has a direct connection with the building energy demand as well, because if the neighborhood has a decreased air temperature, the building a heat gain can go down, and it can eventually impact on cooling load and energy demand and others. So in some way, like understanding the microclimatic condition where the building is located, it's important. So as I mentioned, like I'm focusing only in one part, which is like simulation at neighborhood scale for today's meeting. So my primary question is like how to combine this computational study and the community feedback to basically identify the efficient and socially acceptable urban heat island mitigation strategies at neighborhood scale. And I think the first sub questions is related with outdoor environmental condition. So if we do these interventions, what will be the change in air temperature, mean radiant temperature, relative humidity, air velocity? So the microclimatic condition in this area. So there will be several steps like working with community and the simulation. And for this case, like for the base case, one community, one neighborhood has been selected. So I'm focusing on Broadway East, which we actually visited in 2023, and then selected after understanding the neighborhood, I tried to understand what's the difference between like where there is vegetation and where there's not. So in 2023 summer, I went there with like Kestrel meter and took some measurements in two spots. So spot one is in a parking lot with very less green, you can see, and the spot two is like more green and beside field. So then I collected data from 12 to 4 for up to like 4 in the afternoon. And these are the environmental parameters like wind speed, air temperature, humidity, and heat index that I collected with the Kestrel meter, and it was also collected with the BSEC weather station. So if I see the diagram, like these 1 and 2 are the places where I collected the data. And fortunately, we have a BSEC weather station at spot 3 and at spot 4, which is like CRC and CCA. So Darren shared these data with me, and I'm grateful for that. So from there, I collected the information. Okay, so from the weather station data, what's the air temperature, relative humidity, wind velocity, and heat index is for these 2 spots, and what I collected. So this is helping me to understand the overall microclimatic condition. And I found out in all the cases, maximum, minimum, and average, we see the highest temperature at spot 1, which is the parking lot with no green. And the lowest temperature was near spot 3, which was in a green field and at the shadow of the church. So then I tried to understand these 4 spots in all these environmental parameters. And in both cases, like air temperature and the heat index, the parking lot with no green shows the highest temperature, and the highest relative humidity is shown in spot 2, which is beside the green field, because the humidity is higher there. So from this understanding, now I'm working, I'm trying to create my base model for my NVMet analysis. So I'm trying to see how the neighborhood is, what are the materials is being used, what are the details area. So I started with a smaller area, and then I make it a larger model to cover all these 4 areas. So while doing this NVMet, taking that region, making the buildings, then introducing the surface materials like soil, asphalt roads, pavements, introducing all kind of grasses and trees that we have there. And this is the preliminary base model that I have made for this area. So you can see that this is the neighborhood, the existing condition, and this is what we have in the NVMet model to understand how much is the difference between the really on-site temperature and in the simulated data. So this was simulated on the exact day when I did the field study. So I did it for 24 hours for every hour. Here I'm showing 6-hour difference to see what are the areas where the temperature is raised and how the wind is flowing, what's the condition of the heat stress and others in this selected part. So in this way, actually, this is the overall understanding of how it is changing over the day, either in a 24 hours. And sometimes if it's on the first day, maybe we don't have the previous data. So I also did it with 48 hours so that on the second day, we have also the data from the earlier day, so it can go little closer to the real data. And from there, it's how it is changing over the day in a 48-hour simulation, I try to understand. And currently, I am trying to increase the accuracy of the base model so that I can see the effect of the interventions. So I took one spot, exactly like spot 3, where BSEC CRC data has been collected, and I compared it with my NVMet model. And I see there is a difference of around 5.83 degree. So currently my stage is it's acceptable if the difference is 1 or 2 degrees. So I'm working with the material, surface quality, and the vegetation and other values to make it more accurate. And when I do the more acceptable base model, my goal is to do the introduce all the mitigation strategies in the neighborhood scale, like increasing albedo, increasing green factor, increasing blue factor, and then see what is the effective strategies for this neighborhood. And if we can reduce the outdoor air temperature, it can eventually reduce the building heat gain and lower the energy demand of the building. So yeah, this is my current stage, and thank you for giving me this opportunity again.
Excellent. Thank you. Any question from the audience?
I see Elliot has a question.
Oh, yeah, Ellen, please.
Hey, Tajane.
Mhm.
I'm really interested like in the time series or actually the animation. And I'm curious if you notice there are different times of day when those temperatures become relatively homogeneous versus if you start to see stronger temperature gradients or it becomes localized at a certain time. Right. So essentially, like if you go back to those panels,
Mhm.
oh, it's gonna be hard for I to describe. Maybe I'll say like the lower left,
Mhm.
where those temperatures look fairly homogeneous
Mhm.
versus the one in the upper left, where you see like stronger temperature gradients. What time periods are those?
Actually, these are not like comparable with each other because the range is varied. So, like if I want to compare with by each diagram with each other, the baseline should be same for all criteria. So currently, like if I do like 1 degree difference or like 0.5 degree difference, I can't see exactly what's happening at different like smaller regions. So now these one image is not comparable exactly with another. Yeah, so but that is possible when I reduce the when I make the same scale, like the starting and the ending and the deviation, then we can compare with each other. So I'm like observing both. Here I just showed this version.
Gotcha.
Thank you.
Okay, I think Jason has a question.
Yeah, Desni, thank you. Thank you for the presentation. Very good. I was curious on what meteorological forcing is being used to drive the model, right? To actually kind of flow in. Does it come from like a reanalysis, or is it just kind of some constant wind being pushed through?
It's from climate consultant, and for this location, so there are like different versions. So I'm currently using the basic version where the climate data from the climate consultant, I'm using this. But there are ways to use other data as well.
Okay, thank you.
Thank you.
Okay, good. Yeah, thank you very much. I think we can move to the next speaker, Rawat from Unreal. I think you also a PhD student, right? While you work at Unreal.
I'm also a PhD candidate at Georgia Tech University.
Yes.
Thanks. Let me share my screen. Boy. Can everyone see my screen?
Yeah.
Okay, so I'm gonna be discussing about AI-driven frameworks for characterizing urban energy models. Here's the content of this presentation. So introducing the bottom-up modeling and reverse engineering, the methods that we developed, and how we used these models in a generative way, and the case study for the Baltimore case study. So first of all, to start, so we usually we've been developing a lot of the bottom-up modeling capabilities. So we, from a specific community, we have a lot of data regarding the grid, the building type, geometry, the building system properties, and for all of this data that we collect, we have a model that can physically model it's the behavior of these systems. So for example, like grid systems, we have OpenDSS and RNM and other tools related to the grid modeling. For DERs, we have REOP, for example, and for the buildings, we have Energy Plus and OpenStudio. And we've been developing a lot of these, the bottom-up approach where we first of all, like model the building loads, and then from the loads, we can size and optimize the operation of our DR systems, the batteries and PVs, for example. And then after this, we go use these loads in order to size our electrical distribution network, like the substation, and design the feeder, the transformer, the lines, and the feeder for a specific community or district. So this is a bottom-up approach, which we've been developing the capabilities to do so. And then here we are, what we're working on is to reverse engineer this bottom-up workflow. So basically, what if we have missing data that we have in a real community, which is mainly the case. So how can we impute this missing data using reverse engineering? So basically, for example, let's say we have only the aggregate profile of a specific district, and we only know some information about the grid, the streets, the building geometry, floor area, and number of stories. So how can we model this bottom-up approach, and we have data gaps, missing properties for our to complete our energy models. So to do so, we are doing reverse engineering in order to predict and filling the gaps of missing data and unknown properties and characteristics for our buildings, DERs, and the grid. In order to do so, we developed, first of all, we were using UrbanOpt, which is basically model buildings at a single building resolution, which we have a GeoJSON file that we can get some information from open source sources like OpenStreetMap, Zillow, Redfin, Microsoft Building Footprint, and we can get some information about the buildings from there. We also have RESTOC and Comstock data sets where we have other data, but they are a different scale. So the idea here, we have to do some disaggregation framework in order to fill in the data gaps. So the methodology that we've developed is utilizing deep neural networks. For example, here, if a user will know some of the information about the buildings in a district, let's say they know building type, floor area, number of stories, heating, fuel, vintage, and energy use. So we develop a model architecture automatically, and in order to predict the missing characteristics, and this model can be trained on RESTOC or Comstock data, and then integrated into Urban, and then after predicting the missing properties, we can complete the development of an energy model, which goes into UrbanOpt and for simulations. And then after developing this model, now we can do future scenarios or explore different scenarios and what if scenarios by injecting a target for a specific property. This work have been developed in a module and which will be released soon as an open source where we automate this framework, and we can investigate predict different characteristics. And this here are just an example, but this can change based on the user knowledge of initial knowledge of the community, and what is how to fill in the data gaps, and how to create new scenarios and explore new scenarios with this approach. So basically, this is a two-layer neural network, but also we are dealing with more complex data types. So we have also some projects might have the time series data of a specific building, and some have some information which is numerical, like the total energy use or the floor area, and some categorical information about the buildings. And then in order to predict the missing characteristics with this multimodality of data inputs, we create a more complex or combined, automatically develop this architecture of model where time series data, for example, here is an LSTM, is modeled using an LSTM model and a different branch, and then numerical data also have branch, and categorical data have a branch, and then combined in order to predict the missing characteristics. And then we were validating this approach using different validation techniques. Like this is one, which is the leave one out cross validation, where we have like from the rest of data, for example, we randomly select a building and remove it, and then we start we mask the unknown characteristics. Let's say we only know number of stories, floor area, and building type, and then we are using our method in order to predict the missing characteristics, and then we compare it with the hidden building which we masked and we know the values for. So we tested this. So we did multiple iteration with different knowledge of initial knowledge of our community, and you can see here the like the more information we know, the more accuracy for predicting unknown characteristics. And then we use this injection approach in order to explore new scenarios. For the Baltimore case study, we developed this case study, and we know this information about the building, which we got from Zillow, Redfin, and OpenStreetMap about this community, and then we utilize these in order to utilize our models in order to predict the missing characteristics. And you can see here the predicted characteristics along with some validation metrics for each predicted characteristic. And then we can start doing what if scenarios. So what if we want to target lower energy use targets? So this is, we inject a specific energy use or distribution for the community, and then our methodology will predict the characteristics. So you can see here we did a comparison between two examples where we injected a more efficient or lower energy use target with a high and injection two, which is a higher energy use target. And you can see here the a difference in insulation, which is better in this one. For example, here there is more double pane windows in comparison to the other injection. And then we can put these properties and then automatically generate the urban energy model. And here, finally, this is like a more validation where we compared the injected energy use target versus the simulated energy use. And you can see here for multiple buildings, so our injected target for a specific energy use, or can be other targets like emissions or other properties. We compared it to the energy use, the simulated energy use, and we are within 15% of error for the buildings. You can see here for the high energy use target, this across 5 buildings, and as well for the low, in the injection with low energy use target. Yeah, that's basically a presentation, and please let me know if you have any questions.
Thank you. Excellent. Yeah, that's very interesting to combine with the AI. Yeah. Okay, and any questions from the audience? Maybe I have a quick question. So in this case, your injection is more like a reverse order, right? You have the target, then you want to see what is, and then your simulation is like a forward method. Then you see if you can meet each other.
Correct. Exactly. So this is a new method which is utilizing the model in a different way, which is reverse, because in a deep neural network we can do this because it goes both ways. And then this like we thought this method worked best when we're dealing with data gaps, because you have multiple inputs, you can model multiple inputs and multiple outputs, and can scale with a tool that users like know specific information, and the specific information can vary from one user to another that they know about the community.
Excellent. Okay, I think we can move to the last. Yeah, it's supposed to be my student Rosina, and she has class, so I will present So on her behalf, it's really the students' work. Yeah, so the things I have, okay, is really from the 2 PhD students at my lab. Okay, let me just. Yeah, so the first work was done mainly by Rosina. Yeah, so in this work, we're trying to create the reference building energy model for row house. No, because row house is really the typical buildings in the low-income community in Baltimore. Yeah, we don't know the information, then it's difficult to do the retrofit analysis. So objective to create the model. And then after we create the model, we validate the model using the utility data we obtained from BGE, and then we have the validated model, and then we can study different building retrofit scenarios. This is the entire methodology. As you can see, first step is really develop the model. So we use the existing building stock data, trying to populate the model parameters, and then we generate energy plus model. And then with that, we can do energy efficiency studies, so different building retrofit method. And we can also do the thermal resilience study. For example, as we learned, a lot of row house in Baltimore, they do not have air conditioning, or they have air conditioning, but they don't have enough money to pay the electricity bill, then they choose not to run the AC in the summer. So we want to see what is the impact. And that, I would say the key work here is really to develop the model, which can be representative for the row house in Baltimore. So yeah, then we can validate the model. So this is what we have. We created the row house model. I think we presented in the previous work is the row house, because it's multiple building connected, we have the interior units, we also have the under units. And so what we did here is we collect the BGE data. So the data is really distributed, right? So in a wide spectrum, depends on user behavior. So what we try, so that's why you can see this volume plot. So what we trying to do is for different orientation of the end units, north, south, east, west facing, so that's the different energy consumptions of the model we generated. And so in general, we are able to meet the center profile. So that means our model is able to represent a typical row house in Baltimore. And then when we have this row house model, then we can study the different energy efficiency measure. So for example, so this figure shows the potential energy reduction if we do the building retrofits. So the baseline is based on the model we just validated. The range, you can see the first column is all the baseline data. So here we use EUI, is energy usage intensivity, is the total energy consumption divided by the area over a year. So the range shows different orientations, and certain orientations have higher consumption, and other orientation may have lower consumptions. In general, we can see the building retrofits can significantly reduce the energy consumption. For the under units, it reduces about 49%. For the interior units, it can reduce about 40%. Then we can also see the breakdown of energy reduction. We can see significant come from the heating, which is about 73 for the under units, 75 for the interior units. And also, another interesting finding is that more energy reduction can come from retrofit for the under units compared to interior units, because under units can protect the rest of the buildings. So therefore, if the budget is limited, so then we may consider prioritize those under units. And also, especially those one facing I think the west side has highest energy consumption, which means the highest energy reduction potential. The right figure we compares the EUI reduction of retrofit on the future weather. Here, we use the future weather data obtained from Oak Ridge National Lab. And so the TMY is the typical weather data. Then the future for, they can see from 2020 to 2039 all the way to 2080 to 2099. So again, we can see the different way of energy consumption reduction. And interestingly, we can see the total energy consumption is reducing over the years. That's because the future weather data predict global warming. Therefore, you need less heating because heating is dominated for Baltimore. And so the same trend for interior units. And similarly, we can see that the under units still use more energy compared to interior units. Another interesting finding we can see is that the energy distribution is changing. So initially, as you can see here, if we do retrofit, right, about 13% used for heating, 8% for cooling. But for the future, now you use about 14% for cooling, 6% for heating. So basically now you all kind of flipped. So that means we need to consider that. The part did not change is the other usage from cooking or other so electric device, which is not, we do not have any retrofit measure implemented in this case. So that means in the future, we may also, if we want to further reduce energy consumption, then building energy efficiency measure for other like cooking things should be deployed because now they become dominant. So we also studied the thermal resilience of the house. What we're trying to do here is to understand if in the hot summer, if we don't have air conditioning, but you still have other electricity, for example, you could do cooking, you can do watching TV, do other things. So the temperature may goes up, as you can see, over time. So that will cause some, also temperature change fluctuating with the follow the outdoor air temperature. And another important thing we found that the bottom zone for the under units tends to have higher temperature in this case. So that's because you have cooking or other activity generate a lot of internal heat. And so this figure compares thermal resilience under future weather for all the way from the current typical year all the way to 2020. So you can see we will have increased fatal hours in the future because of the global warming. So that means cooling will be needed. If we consider the safety for the future, for example, those reasons we need to install air conditionings. Or if we want to retrofit, we need to consider that what's going to happen if they don't have air conditioning in the summer. So this work we mainly did is individual home, and then we want to see how can we scale it up. So my other PhD student, Yizhi, did work is trying to develop large-scale building energy modeling. I think similar to Aaron's work, but we take a slightly different approach. So what we're trying to do is, can we generate model for every individual home using those online housing database? So here we call it data-informed building energy modeling. And entire approach is first we also start from survey data, also use the online housing data sets from different real estate website, property and tax database. And then we generate the models. So some information we have and we don't, and then we're using the Bayesian prediction network model to populate the missing information. And then further, then we can vectorize those information, assign them to the different buildings so that we're able to get a good representations. And then we calibrate the model using the actual energy data from the BGE. The goal is to make sure the aggregated data can represent the community. So here, maybe I show the case, it will be easier. We select two communities. One we consider is a disadvantaged community because it's really defined by the low income, the income. And the other one we consider non-disadvantaged community based on income. So we bought 900 buildings in these two communities. So the goal is that can we develop the models for every single building, but then aggregated energy profile matches. So what we first did is to using the k-means clustering, trying to understand the different usage profile. So you see this one is natural gas. You can see the consumption is quite different. If you after clustering, looks like cluster 1, they probably use natural gas for heating. So similar for cluster 4. And then we also did the same thing for electricity. So if you see significant increase of electricity in the summer, most likely this building has AC for cooling. After clustering, then we can distribute those different device type, building type to every individual building. Then we run a simulation. We compare the aggregated results. So this we compared with actual measure data from the BGE. So because of the privacy reason, we cannot do every single building. Therefore, we just select community. In that case, we won't be able to identify which building consume how much. But we have confidence on the entire community. So this is comparison for electricity and the natural gas. As you can see, we are able to really predict the energy consumption, very precisely compared to the utility data. So now we have community building energy models, right, that we can trust. Then when we have this model, then we can do different analysis. For example, you can do the analysis of the buildings under different weather condition if you do retrofits, and so at the disadvantaged community or advantaged communities. So and that you can see the impacts, and then we can decide should we retrofit the window, should we replace AC, and so which measure can have the best effect on the different and which community. So here we list a few ideas. For example, we can even study what will be the peak power demand at which community, so that the utility can decide how they're going to size the substations. Yeah, that's a quick summary of our work. Any questions?
Thanks, Wanda. Real quick, because I know we're running out of time. On Rosina's work, there where you look at the future energy, could you state again, what is the assumption about air conditioning? I know it's motivated in part by the fact that people don't have the ability to put on air conditioning. So how does that work into the projections?
Yeah, so here we still assume people have everything else. They have heating, they have cooking, everything. So then okay, if you say energy, oh sorry, let me move here. Yeah, yes. So okay, so this one, no, sorry, I want to make it clear. For this one, we still assume they have cooling, otherwise the cooling would be zero, right?
Right.
Yeah, so we do, they assume they have AC. So then what's happening if you retrofit? Yeah, then for the thermal resilience, we assume they don't have AC. For townhouse, they don't have AC.
I see. So this one is showing no AC danger. The next one is showing with AC change in energy usage.
Yeah,
Okay.
energy, yeah.
Great, thank you.
Yep. Any other questions? Okay, looks like we are perfect on time.
Amazing, really well done. Thanks, Wanga. Thanks to the whole team for those great presentations. Really excited to see this work. And we are out of time, but I'm sure people are gonna follow up. It's great to learn more about the work of the Buildings and Energy team. Have a great day, everybody.